Hello again, everybody, and welcome to the sixth and final video in our right triangle trigonometry series. Today we're going to look at solving problems that involve more than one right triangle. So just as with the previous video, I have nothing new to really teach you, but it's just how to kind of get through these problems we're going to look at. So if you're wondering what that title meant, it meant what this thing looks like. There's two right triangles, and sometimes they're joined or sometimes they're on top of one another, like something called nested. And nested, by the way, would look like this, where you have one big triangle and then you have like a smaller one resting right on top. So those are the two types that we're going to look at. So let's just get right into the problem. So we're looking for side CD. So that is right here, side CD. So now we don't want to create more work. So if you can find it right off the bat, do it. And if I look, well, I have an angle, and that's important. And then I have this one side I'll be looking for, but I need to know, one of the other sides. Meaning I would need to know BC or BD. If I had one of those two sides, I would be good to go. But I don't, so I'm not. So that's where we have to get into this other triangle. So in this triangle ABD, now that I'm in that triangle, we have to look to see, well, what can we do? Well, if I could use this, I'm going to call this triangle 1. If I can use this triangle to find this side length, then in this second triangle, I could use that side length again and get to 20, or end with that angle of 26 degrees to find that x. So that's what we're going to do. I'll call this one y. I'm going to find y first using this first triangle, and then I'm going to use that dimension again in that second triangle because they're joined and I can, to help me find that angle or that side length x. Okay, so let's get doing that. So the first thing, in triangle ABD, again, this is the first time I'm mentioning it, but I'm writing that down just for organization, just so you kind of know what I'm working with. Okay, so in that triangle, and I've kind of made a bit of a mess out of it, so I'm sorry about that. But remember, we always start with locking in our angle. And now that I've locked that in, I can name everything. So this would have to be the opposite leg. And this over here, my y, would end up being my hypotenuse. So if you remember from that previous video, SOHCAHTOA, I have opposite and hypotenuse, so I'm going to use sine. Okay, so, let's go to blue. Sine 47 equals 4.2, and I just called it y. You can use whatever variable you want to use, but that's what I chose. Cross multiply. Sine 47. That's going to be 4.2. Now I want to divide by that sine 47 because I want to move it to the opposite side. You move it to the opposite side by performing the opposite operation. And initially that was y times sine 47, so that's why I did it. Anyway, so now I have to divide that to figure out what y would be. So that would be 5.74. Okay, and I've got a lot of different things going on here. So I'm just going to erase all this right now. Yeah, I learned how to do that, people. And then this would, I'm going to write that in a different color maybe. So 5.74. Okay, so now we use that in this second triangle. The second triangle, so this would be triangle, I guess, BCD. I'm, once again, I'm going to use a different color. Sorry, guys. I'm talking to myself a lot in this one. I want to lock down my color, I want to lock down my angle. So I'm working with this 26 degrees. So now that I know that, the side I'm looking for ends up becoming the adjacent leg because it's the leg right beside it. And the 5.74, if you notice, it's right across from that right angle, so that ends up being the hypotenuse. So I have an adjacent and a hypotenuse. That means cosine. I don't think we've had to use cosine much lately. Anyway, so cos 26 degrees equals my adjacent, which is x, over my hypotenuse, which is 5.74. And great news, the variable's on top, so that means it's the quicker version of this solution. So 1 times x is x, and then 5.74 times cos 29. Or 26, I'm sorry, that'd be a mistake. Once I multiply that, I get 5.16 centimeters. And that is what I was chasing, because remember our x is that CD, that side CD. And that is how you'd get through that example. Let's look at another one. Okay, again, you can see these are two right angles now, or sorry, two right triangles. You might not realize why. Here you can see clearly is the one right angle, but that means this one's also a right angle, okay? How do I know that? Well, this line here is horizontal and this one is vertical, so that means they meet at 90. That's true, but also when I have that horizontal line, you could call that a straight angle, so it has to add to 180. So if I know part of it's 90, that means the other part would have to be 90 as well. Anyway, where is this XY that we're looking for? It looks like it's right there on the side. Okay, this is the same problem as before, where it's like, if you could find it directly, do it. Like, don't beat around the bush, let's just solve that thing. That would mean I'd have to know this side XW or this other side YW. I don't know them. So because I don't know them, I'm stuck. So this is where I go to this other triangle. And I can find this angle using I can find that side length using that that angle 20 degrees. Sorry, I don't know why, I'm just starting to mumble there. Okay, so let's start doing it. Let's not waste any time, people. So my first step in this triangle, I'll call it ZWY, is I'm locking down my angle, that's 20. So that means this guy is opposite, and then I've noticed this is across from my right angle, so this would be my hypotenuse. So what is opposite hypotenuse? Sine. So I'm going to use sine 20 to end up finding that opposite side, which I got to give it a variable. I haven't given it a variable yet. I'll just use y again. So sine 20, which is y over 8.4. And then again, the variable's on top, which means I kind of did that backwards. I always bring my variable to the left side. So it'd be y times 1 that way, and then now 8.4 times sine 20. I think I didn't finish my last thought. Just remember when the variable's on the top, it's the shorter version. You don't need to remember that actually, just that's the pattern you'll notice. Anyway, 8.4 times sine 20 ends up being 2.87, and looks like that's centimeters. So then I'm going to use that. Okay, and it's hard to kind of see what I'm doing there. So again, I'm going to now just kind of get rid of some of that stuff. I'll use red. So this is 2.87. So now in my second triangle, triangle XWY, I can now find that side X, because I've given myself a side length from this triangle. So what am I talking about? Kind of mumbling again. So I'm going to use this 20 degrees, which is really there. Now I'll start naming everything. So this would be the adjacent side, or the adjacent leg. And then this X ends up being the hypotenuse, because it's across from my right angle. So adjacent and hypotenuse, that is cosine. So cos 22 is equal to the adjacent side, which is the 2.87. over the hypotenuse, which I will call x. And there we go. Now I just have to solve for that, and I'll have this question done as well. So x times cos 22 equals 2.87 divided by my cos 22. So then x equals, and yeah, 3.12. Sorry about that, guys. 3.12 is what I got. I'm sorry, I wrote 3.12. I meant to write 3.10. So you might have been doing that at home, and then you've been like, hey, what just happened there? That should be 3.1 or 3.10. Sorry about that, and that is my final answer. Now in this third example, we're going to switch things up. Now we have this nested type. So in the nested type, you just need to know that I have two triangles. So I have this one smaller one, which would be A, B, C. Then I have one larger one, which would be A, B again, D. Okay? Now, what really happens is this smaller one is sitting inside this larger one, and it just gives you that kind of neat effect. CD. So what we're actually looking for is that there. So the way we would find just that segment is we would first of all find the entire length, so that BD. So that would be up here in this triangle. Then what we can do is, using the smaller triangle, just find that BC, which I can do up here. So again, let me just color code this properly. So this is the BD, this is the BC, and then once we're done that, we can simply subtract and figure out what the difference is between them, and that would be that leftover portion. So that is how we will do that. And when you're dealing with nested triangles, that's often the technique. You'll find like a large, maybe it's a large angle, and then you find a smaller angle, and that will tell you the leftover angle. Or like this, you'd find the large line, then the small line, then you can find the difference between the lines. Anyway, the order you do this does not matter, because you just need two answers and you'll subtract them, so it really doesn't matter. I will go with the large one first. I'll go triangle A, B, D. Okay, so I'm going to use what I've kind of drawn up top. So this is going to be 4. We know that's 90. And then the angle, well, the angle is the entire thing. So this ends up being 52 degrees. That's supposed to be a 5. We might as well fill in the stuff in the smaller one. So this would be 4 as well. And then the smaller, though, angle is just 20. That doesn't look like a 52. Is that? Yeah, that looks better. There's a 52. Okay, so I need to find down here, I guess I can just call that X. I always work from my angle first, so that's my angle, so that means this is opposite, and now I see this is adjacent, so that's going to be tangent. Opposite and adjacent, tangent. So tan 52 equals X over 4. And then just solve away. That's X. 4 times tan 52. 4 times tan 52 is 5.12. And that is centimeters. So that is the large one, okay? That's BD. In the second one, and I can even write that, BD. In the second one, this is now triangle ABC, the smaller one. And again, I'm going to lock in my angle, and I'm looking for this guy there. I guess I'll call it Y, just have a different variable. And you'll see it's really the same situation. This is the opposite. This is the adjacent. So I'm going to end up using tan one more time to find this. So tan of 20 degrees. The opposite is Y. The adjacent is 4. Again, variable on top. That's great. That means it's the shorter one, so that's just kind of nice. 4 times tan 20. All right, and then 4 times tan 20 ends up being 1.46 centimeters. Here comes my third step. Now I want to find, that is CD. So to find CD, what we have to do is simply subtract. So CD would be equal to 5.12 minus my 1.46, and that's going to be the difference. So like I explained there at the start of the problem, which ends up being 3.66 centimeters. And that is how you deal with a nested problem in which we just need a portion of a line, not the entire line. Okay, another nested problem. So once again, I think it's smart. Let's just draw this out. So hopefully you see that there is a kind of shorter triangle. So that would be B, C, A, and this is my right angle. So this is 7, this is 13. And then I have a larger triangle. I'm not drawing this perfectly to scale, but that's okay. And this would be D, C, A. So now, if you look at DC, DC is this entire thing. So it's going to be 3 and 7, so that makes it 10. This would still be 13. Now, what are we actually trying to find? I kind of just jumped to breaking up the triangles, because that's always a nice step. We're trying to find angle DAB. So DAB would be, you start at D, you go down to A, and then up to B, meaning we're finding this angle right here, everybody. We want to find right in here. Well, how can we do that? Well, it's going to be this kind of classic trick that I just looked at last time, where what we can do is use a large triangle and find the big angle A. So that's the whole thing. Let's use a color here. Let's say green. Okay, so I'm going to find all of angle A, so right here. Then I can use the smaller triangle and find the smaller angle A, which would be right here. And then once I subtract them, I'd be left with that blue shaded area, which is the DAB. Okay, so that is what I will do. Once again, there isn't a right or a wrong order to do this. You just have to find both answers and subtract. Big number comes first, then small number. So let's get rolling here. I'm in this first one. I will work with my triangle that's right above it. So that is going to be BCA. And I'm going to be looking for this angle A. And so if I'm looking for angle A, that means I want to work from angle A. I like when these are different colors. So that means this is opposite. This is adjacent. So tangent, that pops up a lot, that tangent. So tan A equals 7 over 13. So now I have both my side lengths. I'm looking for that angle. Remember, when you're looking for the angle, you have to go inverse tan. You're telling your calculator, hey man, go backwards on that chart and find me that angle given this angle, or sorry, this ratio. So that ends up being 28.30. Okay, that's what that smaller angle would be. Now in the bigger triangle, DCA. We're going to find A again. So tangent A, and I kind of jumped to the conclusion there that it's a tangent because you can see this is opposite. This is adjacent, so we have the same deal. So tangent A is going to be equal to 10 over 13. Okay, so angle A is equal to inverse tan, 10 over 13. What does that end up being? 37.57. Okay, now step 3, we actually want to find angle DAB. And that thing is equal to my larger angle, 37.57, subtract my smaller one, 28.30. So that works out to be 9.27 degrees. So just a sliver of an angle. But that is how you complete that. All right, so you've kind of seen the main, in your textbook, that's kind of the main types of problems you'll look at. Let's just do one more example. Just a situational problem. And we'll read this thing first. From the top of a 20-meter high building, a surveyor measured the angle of elevation of the top of another building and the angle of depression to the base. So when it says of the base or of the base and of the top, that's the way your textbook likes to write them. I just like seeing it as to the top and to the base, which is the bottom. The surveyor sketched this plan of her measurements, determined the height of the taller building to the nearest tenth of a meter. So I want to know, in the end, I want to know how tall that building is. Okay, so we need to add some things in. What's going to stand out? I'm not sure. Maybe yellow will. Well, the first thing to notice is that right here, this has to be 20 because this is 20. And here's a horizontal line, meaning they're the same height. So I know a little bit more there. I want to know the total height. So really, that means I know that's 20. If I could figure out that section of it, I could then add 20 plus x from these two different triangles. Now, I want to know what x is, so can I go right to it? Well, if I look at this top triangle, and you know what, I want to stop for a second. I'm going to give these some letters, just so it's maybe less confusing. A, B, C, and D. So if I'm in this triangle ADB, I want to find that x, and I don't have enough information. I have an angle, which is 30, and I know I will want to look for side AD, but I don't have another, I think I might have said angle there. I want to look for side AD. But I don't have another known side. So, what could I use? Well, I'm going to use that same logic as we did in our first and second examples. When I go down to this other triangle, CDB, I can use that triangle to find that leg, Y, and then I can reuse it in that other triangle. So that is what I will do. That's how I'm going to get through this problem. So I have to work with the smaller triangle to find that Y first. So in triangle CDB, just so we know, CDB. Okay, I'm going to lock in. I'm working from this 15 degrees, which means this guy ends up being opposite, and then this ends up being adjacent. That Y ends up being adjacent. So opposite and adjacent, which is tangent. So tan 15 degrees The opposite is 20 over y. Okay, and then now once again we just start solving. So put that over 1. Y times tan 15 equals 20. Divide by tan 15, divide by tan 15. Y ends up equaling 74.64. And that is meters. So the distance between the buildings is 74.64 meters. So now I can use that in this second step of my solution. So now I'm in this triangle ADB. And let's just scratch this out because that's so small anyway. And that's 74.64. When I'm solving this, what's a nice color? I'm going to go with red. I'm going to lock in my angle. So that's 30. So from 30, I would now call my x the opposite, and I would call this 74 the adjacent, and I'm using tangent again. Man, it seems like we're using tangent a lot. Anyway, so tan 30 equals x over 74.64. So that's at least nice. The variable's on top, meaning it's a little bit quicker. X equals 74.64 times the tan 30. All right, that ends up being 43.09. And that is meters. So now I know those two components. So the third step for the height, it's simply going to be equal to adding those two things up. So the 20 plus the 43.09. So just in case you're wondering, the 43.09 goes right there. So that ends up being 63.09 meters. Now it says nearest tenth, I guess, as I look at that again. So I guess 63.1 meters. All right, guys. So that is a sampling of problems that involves more than one right triangle. I hope that made sense. If it didn't make sense, make sure you talk to myself or get talking to a teacher. Otherwise, everyone, have a great night.